Good morning, good afternoon, everybody. So I'm Rakshith Krishnappa. So I will be presenting Module 3 of Performance Portability and Productivity today. For people who have been attending the previous session, so this is Module 3, what we are on March 9th. In the first module, we covered some introduction. In the second module, we looked at some optimization methods. And then today we will mainly be looking at optimization for performance portability so that the code can run efficiently on both CPUs and GPUs. And then next week, we will have a kind of an open house, and anybody can come with their own code, and we will help you to make your code performance portable across CPUs and GPUs. Right. So just a recap of what we did in the first module. We will once again quickly do a recap with the code as well. In the first module, we actually looked at what is performance portability, why is it important, and we implemented a basic gem algorithm in SYCL, as well as using the math kernel library. And we did some analysis and collected some numbers on various hardware, 2 Intel GPUs and then 2 Intel Xeon CPUs. In last month's session, we took that basic SYCL code that we had written and did some performance tuning, looked at what is ND range kernels, and how to use a private memory, and also how to use a shared local memory. And again, we did some analysis and then looked at the results in Intel Advisor Roofline and also Intel Vtune Profiler. So in today's session, we will take the code we have done. We have created various versions of code optimizations, and we will look at how to optimize it further so that it's performance portable across CPUs and GPUs. We will again analyze the results and look at the results on Intel Advisor Roofline and also Intel Vtune Profiler. We will look at how the different accelerator hardware characteristics and how it affects the performance, and we will understand how to how the impact of different varying workgroup size will affect the performance, and we will look at more advanced tuning using the oneAPI GPU optimization guide. Right, so this is what we will look at today. So let me switch over to the Intel Dev Cloud. Okay, so if you I think most of you have a Intel Dev Cloud account signed up if you've attended the previous session. So if not, please go to devcloud.intel.com/oneAPI, and then you can log into the account. And once you've logged in, you can click on this option called connect with Jupyter Lab. So if you do that, you will see an interface similar to this one. Right, so this is Jupyter Lab. On the left-hand side, we have a bunch of preloaded modules in various different domains. And today, what we will be looking at is this second folder here, DPC++ performance portability. All right, so if we click on this folder, we have a bunch of Jupyter notebooks, and mainly I'll do a quick recap of what we did in the first and second session. So the first one, I'll skip the introduction. Let's get into the first notebook here. So this is we did in the first module. Mainly we implemented a basic gem algorithm using a math kernel library, and this document gives you some introduction about what is math kernel library and how it actually works. And we have a basic code implementation that we looked at, and you can see that we have matrix A, B, and C, and we create buffers for that, and then we use just this one line of math kernel library to actually calculate the matrix multiplication output, right? And we looked at how to get the roofline reports for the same, as well as we also looked at the Vtune reports, right? And once we had that output, we also looked at how to implement matrix multiplication with just basic SQL programming, the very simplest form of implementation. So you can see that if you're not using a library, we can also implement this using a basic parallel kernel, and then we have just a for loop within that, which will actually calculate the matrix multiplication output in matrix C. Right? So once we did this one, we also looked at how the performance between the two implementation, one using the basic implementation and also MKL. And you can see that as the matrix size goes higher and higher, the basic implementation is very slow compared to the math kernel library implementation. So this is what we did in the very first session of the series. So in the part 2 of the series last month, we looked at further optimizing. We learned about ND range kernels, and instead of using one big matrix, we actually group them into smaller groups, and then we use these groups to calculate the output for each group and then aggregate the results. So that's what we did in this second implementation. You can see that instead of using a basic parallel kernel, we actually use a ND range. We specify a global size and workgroup size, and then we calculated the output. And then we also looked at slightly different approach where we do the same ND range kernel implementation, but make use of private memory. You can see that in the first implementation, we have a for loop here from 0 through n, and n can be anywhere from like 1024, or it could be like 10,000, right? So for every iteration in this loop, we can see that the actual global output is being updated, right? So every time for every iteration, it's actually accessing the global memory. So there's one way we can avoid this multiple writes by making use of private memory. That's what we looked at. So instead of writing directly in the loop, we actually define a temporary variable, and then outside the for loop is where we are writing to the global memory. And we have an implementation that we looked at last month using private memory, and then we again calculated the did some analysis, and then we can see that the output between just using ND range versus using ND range with the variable for private memory, you can see that there is a slight improvement in performance. Right, and then along with this one, we also looked at a local memory implementation. So this is mainly each subslice in the GPU hardware usually has its own local memory where the workgroup can access it. So accessing from local memory will be faster than accessing from global memory. And we looked at the implementation using local memory here. And you can see that we defined local accessors here. We defined two smaller matrices, call it tile A and tile B, and that is what we use for computation. So this one will further improve the performance. You can see that if you just compare the previous version, the ND range with private memory and local memory, you can see that as the matrix size increases, we can see that there is a almost like 50% performance improvement just by using the shared local memory. So these are this is what we looked at in the previous two modules. And today what we will look at, we will try to analyze all the implementations and see what kind of further improvement we can do, right? So it's mainly we will look at this notebook number 4, which is performance portability. right? So just looking at a recap of what we have done so far in the first two modules, you can see that we have 4 different implementations here. The ND range, just basic, and then we have the ND range with private memory, and then we have the one that uses local memory, and also we use just the math kernel library, right? So you can see that just by using fixed workgroup size, we can see that there is slight improvement with every implementation, but you can see that we are still seeing that the implementation using the library is more efficient. What we've done is we've normalized the performance with the MKL implementation to 1, and then based on that we have drawn this graph relative with the relative performance values. You can see that the local memory implementation is the closest we have so far to the math kernel library, right? And just looking at the hardware characteristics, right? So we have 4 different hardwares that we actually used this implementation and tested this. We have the Gen 9 GPU, we have the Iris Xe Max discrete GPU, and then you can see that I think these two are labeled incorrectly, but then you can see that this actually shows you what are the characteristics of the hardware, right? So in the first one, we have 24 EUs and 96 EUs, and the 2 CPUs are 12 cores and 16 cores. And then the local memory size on the GPUs are 64, and then the CPUs are 32. And you can see that the max workgroup size that is allowed with various hardware actually varies, depending on the capability of the hardware. So this is something that you can query and get using SQL device info, or you can also use just CLinfo to actually find out what's the max workgroup size that can be used. So to look at that, let me, what I've done is I've already logged into 3 different hardwares right here. So the first one I have is I just did the CLinfo to find out what kind of hardware I have. And you can see that the first one just has a Xeon CPU. So this is the device we'll be running the code on. And then we have another terminal here where we have logged into a Gen 9 device. So it has a Xeon CPU, and it also has a Gen 9 GPU here. And then the third one that we have is, again, Intel CPU with a dual Iris Xe Max graphics. So we'll use one of these to compute the matrix multiplication. So if we quickly want to see the hardware characteristics, we can actually just run our code right here. So let me compile. So the way we compile is we have the common code, and then we also have the actual implementation. So in this example, I'll just use the, let me just use the ND range maybe. Right, so I'm compiling. Right, so once this is compiled, you can actually execute the code. So this will actually just run on the CPU, and you can see that by default it uses the size 1024, and then it's using a workgroup size of 16 by 16, which is 256. So if you want to change the matrix size, we know that we have a command line option, so we can use a matrix size of 5000 by 5000 and use the workgroup size as 16 by 16, which is 256. So let's quickly run that. So you can see that if we use the workgroup size of 16 by 16, which is 256, right? We get the kernel execution time is about 14 seconds. So, but you can see that the max workgroup size in case of this CPU that we are using is actually 8192, but we are only setting the workgroup size as 256 because we used that as a default because that seemed to work on all the devices that we were using under test. But then if you have to optimize it for a specific hardware, it's good to take into account what is the max size, right? So we can actually, you guys can try this on your end as well. So we can change this to any value, right? So we can also try, let's say 32, for example, and we can compare the performance. So you can see that it's again trying to multiply 5,000 by 5,000, and then the workgroup size here in this case is 32 by 32, right? Which is 1,024. And you can see that you know, we don't see any significant performance improvement there, but you can also go and then change it to let's change this to 64 and try. So again, we're getting about the same performance here. So we can keep on, you know, changing these values. So let's try something like 128 and then see what happens, right? So you can see that 128, we tried to set it as 128, we got a exception error, right? Because 128 times 128 actually exceeds the max value, which is 8192, right? So we can try another value. So a simple way to find out what is the maximum we can use is we can just do a, since we are using two-dimensional values, right? So we can actually just do a square root of 8192 and then see what number we can use. So we can try using, let's say 80, right? So 80 will also be a valid size. So let's see the performance in that case. Right. So you can see that when we used 80, the performance is actually worse than 64, right? So so there is no universal rule that the maximum size will always get you the best performance, right? So it's more about trial and error, and you can see that if it's a multiple of 8 or if it evenly divides the matrix size, you usually end up getting better performance. So you can try with the various different workgroup sizes. We can, so in this example, we used the ND range with private variable. So let's try the local memory version, right? So I'm compiling the local memory optimization. So again, we can start with the workgroup size of 16 times 16, which is 256. Right, so you can see that it's 3.5 seconds here, the kernel execution time. So we can try with 32. See, and we can see that significant improvement if we use a bigger workgroup size, which is 2.25 in this case. So let's try 64. You can see that it's further improved here. It takes 1.45, right? So let's try with size 80, right? So here you can see that size 80 actually worked with the previous implementation. If you look up here for the ND range implementation, 80 by 80 actually worked, right? No issues there. But then in case of local memory, you can see that 80 by 80 is actually failing. And then the reason for it is CL out of resource, right? So if let's look at the code and then try to find out why it is actually failing, even though 80 by 80 is a valid workgroup size, right? So out of resource usually means it could be that it's running out of memory, right? So we are trying to allocate more memory than what is available on the device that we are using. So you can see that in the local memory version, we are allocating tile A and tile B in the local memory, and then you can see that the size of each tile is m times m. So in this case will be 80 times 80, and then each one of these element is a float object. So if you do 80 times 80 into 4, and we are allocating 2 of those for tile A and tile B, right? So let's so we can do a quick calculation here. So let's see, we have 80 times 80 into 4 bytes, which is float, and then we are using 2 of these tiles, right? So if you do that, that's almost 52 kilobytes of memory. And the reason why it's failing is because the CPU has only 32 kilobytes of memory. So the way to look at that is if you just do CL info, right? And then you can see that the local memory size is actually 32 kilobytes. So that's one of the reasons why we are actually seeing a failure when we use a bigger workgroup size, right? So in contrast, you can actually look at the previous passing condition, right? So let's reset this thing. Okay. So we used size 64 that actually passed. So if you do 64 times 64 times 4, since it's float, and then we are using 2 of those tiles, which actually comes up to 32 kilobytes. So that's one of the reasons when you're using local memory, the workgroup size might also become a limitation. So in this case, you can see that. So if we use a size 64 times 64, that's the maximum workgroup size you can use. And then in this case, we can see that 64 actually gives you the best performance when we're using local memory. So we can try this same example on GPUs as well. So let's try. So in this case, we are using the Gen 9. Is this? Yeah, so we are using the Gen 9 system here to execute. So let's set the matrix size to 16, right? So 16 times 16 is 256. So if you guys have logged into DevPlot, please go ahead and then try different values, whatever makes sense. And then let's see what output we can see. So in this case, you can see that it's taking about 9 seconds for execution. So let's try 32, right? So and you can see that it straight away fails, saying that it's invalid workgroup size because the maximum is 256. 32 times 32 was actually executes that. It's greater than 256. Okay. So the other option that might actually work, maybe a smaller workgroup size. right? But if you use a smaller workgroup size, the performance has actually decreased, right? It's taking about 9.5 seconds here, whereas when we use the 16 times 16, it took 9.1 seconds. Right? So you can see that when we start trying out all these different workgroup sizes, we see the performance numbers actually vary. So it's very important to find out what is the most optimal workgroup size to use. So before we, come up with an algorithm for that, let's look at one more hardware, right? So let's look at the Iris Xe Max hardware here. So let's try to run the same local memory implementation on the Iris Xe Max GPU. So again, we'll start with a workgroup size of 16 times 16, which is 256. So here you can say that it's taking 11.3 seconds. You can also see that the max workgroup size here is 512, whereas in case of Gen 9 GPU, it was 256. So which means that there is still room for having a bigger workgroup size, right? So we can try something like 32, right? Which will probably fail because 32 times 32 is still bigger than 256. So another value we can try is you can try something like 20, because 20 times 20 is 400, which is still within the max value. So looks like this is working. So we're using size 400, right? Again, you can see that we have, it takes about 9 seconds here. Let's try 16 one more time. How much did that take? Eleven seconds. So we can try other values too, like say 10. You can see that doesn't give you that good of a performance. We can also try 8, for example. Right, so you can see that this gives takes about 22 seconds, right? So based on all this experimentation, we can see that we tried it on 2 GPUs and also 1 CPU here. You can see that it really depends on definitely having a bigger workgroup size will give you a better result, but it also depends on what size we are picking, whether it's divides equally by the matrix size or not. So for example, on the CPU, we can try, we tried size 32, right? So let's, you can see that it takes 2.25 seconds. So we can also try an odd number, right? So something like 33, right? So even though it's it's a bigger workgroup size, you will get significantly lower performance because we are using an odd number, and since it does not equally divide by 5120, right? So That's one of the other characteristics that actually is important in picking work group size. So it's always better if the work group size that you're picking kind of divides equally by the global size that you're using, and it's also better if it yeah uses the it also divides equally by the maximum value that you have, right? So if we take all this information, right, calculate the performance based on the workgroup sizes, and then we can plot all the values. We can see that this is one example where we looked at in case of Iris Xe Max GPU. You can see that we chose a 20 by 20 is the maximum we can use, and that actually gets lower performance than say 16 by 16, and then you can see that 10 by 10, and then also we have 8 by 8. So just by analyzing this results, we can see that just having a large maximum value for workgroup size does not always get you the best result, but you can see that 16 by 16 and 8 by 8 gives you better performance, mainly because it divides equally by the global size as well as the maximum workgroup size, right? So in case of CPU, you can see that again, the best results are something that is a multiple of 8, or it also divides equally, right? 16, 32, and 64. You can see that it's significantly better performing than other values. And then in some cases, even though 80 by 80 is a valid workgroup size, it's running out of local memory resource. So this is what we looked at, right? So far, what we had done was when we did the comparison of all the different implementations, we used the same workgroup size of 16, right? So what you can see that just by doing experiments with different workgroup size, you can see that using 16 in case of CPU is not the best performant code. So you can actually go up to like 64, which gives you the best performance. But in case of GPU, 16 was a good number, right? Using 16 by 16. But in case of CPU, we have to use a different workgroup size to get better performance. So using this information, we can actually write a piece of code, right, that will automatically pick the best value for CPU if you're running on CPU, and then if you're running on GPU, again, it picks the best value for GPU. So let's look at a slight modification to the code, what we can do. So what we've done is first thing is we try to find all the valid workgroup size to try performance, right? So what we do is we query the device and get the max workgroup size, and then we're doing the same thing. We're trying to find the square root of that number. Since it's a 2-dimensional array, we need to find the value that divides equally on 2 dimensions. So once we get that, we we start incrementing by 2, and then making sure that it actually divides equally by the global size, right? And then this will actually print out all the valid workgroup sizes. And then based on all the valid workgroup sizes that we have to find out which is the most optimal workgroup size. So the way we have done in this case is we actually find out which of these valid workgroup size are divides equally by either 8, 16, or 32. And based on that, we get we've noticed from our experiments that we get better performance, right? So based on that, we actually calculate what is the optimal workgroup size to use. So if we actually do this one, the output will be generated something like this. So in the previous example, we were just printing out the max workgroup size, matrix size, and then directly computing the results. But in this case, we are printing out 2 more additional information, which is we are printing out all the valid workgroup sizes for this hardware. You can see that the valid workgroup sizes are 80, 64, 40, 32, 20, and so on, right? But then the optimal workgroup size that is picked in this case is actually 64 by 64, even though there is a higher valid workgroup size, we are still picking 64 because based on our experiments, we know that a multiple of 32 will actually give you the best result. And we have just used a simple algorithm to actually optimally pick a workgroup size. And then that's what gets used in the application. And then we can actually recalculate all our performance numbers. So let's look at the code modification, right? So this code modification is actually available in the common code, which previously we were using dpcpp common.cpp, and then we have a second one, which is the underscore workgroup. So this has the workgroup implementation. So let's look at these two code examples. You can see that this is what we were using so far. And then we have the workgroup optimized code. And you can see that we have this section of code added, right, which will calculate all the valid workgroup sizes, and then it prints out all the valid workgroup sizes, and then it tries to find among the valid workgroup size, it tries to find the most optimal value, right? So this piece of code from line 77 to 102 is what we've added to make it performance portable for both CPU and GPU by picking the right workgroup size. So now what we can do is for all these examples, we can, instead of using this common code, we can start using the workgroup common code. So this will actually pick the right value for you instead of always picking value 16. So you can see that if you use the regular common file, so let's use a size 5120. By default, this will actually pick 16 by 16, right? So this is what we were using so far. But now if we try to compile the local memory, but instead of using this common file, we will use the other underscore WG common file. So this has the performance portable implementation to pick a workgroup size. So now if you try to run the output with just the default workgroup size, you can see that it actually picked size 64 by 64 instead of just picking 16 by 16, right? So you can see that all the valid workgroup sizes were calculated, and then it picked the optimal workgroup size. Since it's a CPU, it can go up to 64, and it calculates the performance based on this workgroup size. So we can try the same code here, right? So let's not enter any workgroup size. So this screen you're looking at is the Gen 9 GPU, right? So if you run it on Gen 9, it'll still pick 16 by 16 because that is the maximum you can go on Gen 9, because the max workgroup size here in this case is 256. Right, and then let's look at the IrisX Emacs. Again, here you can see that it calculated the valid workgroup sizes, and then in this case, it's actually picking 16 by 16, even though the 20 by 20 is a valid workgroup size. Yeah. So let me know if you have any questions. So hopefully you were able to do the same experiments, right? And then you can, use this kind of a custom algorithm to find out the optimal workgroup size, based on the global size um, as well as the the max workgroup size for the supported device. So that's one way to calculate. So with that, so implementing this performance portable code, then you should be able to recalculate your, all the performance values. And then if we chart it up, you can see that just by, optimizing it for workgroup size, you can see that the local memory implementation now actually is performs much better than the math kernel library implementation, right? So if you look at this chart here, and then if we go scroll up and then look at the chart before local memory optimization, you can see that the performance was much lower, right? So the math kernel library implementation was still the best performing code. But then if you start doing these optimization, you can see that, yeah, your own implementation, manual implementation can actually outperform the library's performance. Then you can also see that, so this particular chart, I think, is for matrix size of 20,000 by 20,000. So there's also multiple graphs here for different matrix sizes. Mainly, I think if you use 1024 by 2024, we don't see a significant we don't see a significant performance improvements. It's as and when the matrix size goes higher and higher is when the optimizations actually give you much better performance. So here you can see that as the matrix size goes higher and higher, the local memory implementation what we have will actually give you much better performance than the math kernel library. So it's always tuning the code based on specific hardware can actually get you much better performance. Right. So let me know if there are any questions on the implementation so far, or if you need time to work this out, try out different values, you can do that. If not, there's another thing for workgroup. To pick the workgroup size, we have there is a calculator that you can use to actually pick the optimal value, which is what we will look at in the next section. So far we just looked at, based on different hardware, we looked at how to optimize it for workgroup size. So there are various different optimizations you can do. We have a GPU optimization guide available. So if you click on this link, so there is a whole document available which will allow you to look at various features and how to optimize it based on that. We can look at reduction, subgroups, and how to avoid register spills, how to optimize based on shared local memory, removing conditional checks, like all these, right? So all these optimization techniques are available in this guide. So if you click on this guide, we make the size a little bit bigger. So yeah, you can use this as a way to navigate and then look at how to further optimize your code. So mainly the most important section is in this kernel subfolder here. So this will allow you to look at various aspects of your kernel, whether you're using reduction, for example. This will give you a detailed documentation on how to how reductions work, and then how to actually optimize it using various techniques, either using atomics or using whole reduction objects. Yeah, again, there's a whole section on subgroups, which will tell you in detail how subgroups work and then how it can be used for further optimization. And let me open up one more. So and then we also have a simple static calculator to calculate the occupancy of a GPU. So if you think the way to do this is you can just search for Intel GPU occupancy calculator. And this will actually give you a simple static calculator. This will help you how to pick the workgroup size, right? So mainly what this will allow you to do is pick a GPU. So either in this case, we have a Gen 9 and we also have a discrete GPU. So you can pick a GPU, right? And then pick the exact type of GPU you have. And then you can select the global size of your application. And then by default, it uses 256 in this case. You can select the subgroup size, and then this will actually tell you based on what workgroup size you use, how much occupancy, the GPU occupancy is used, right? So this, you can also vary the local memory usage. So the more local memory you use, you can see that the occupancy actually decreases at the smaller workgroup sizes. So if you start increasing this one, you can see that if you increase, if you're using a lot of local memory, then the occupancy, the maximum occupancy you can use is around like 25 or so. Right? So it's a useful tool, which will actually give you like all the valid workgroup sizes, and then what is the occupancy you will get based on what workgroup size you're using. So this is something that you can look at. So this particular calculator is also part of the optimization guide. When you go into the section learning about how to use, how to pick the valid workgroup size, you will come across this static calculator, and that's something you can use to tune your code as well. All right, so I will put this link. It's also in the Jupyter notebook right here. So this is something that is very useful that can be used for optimization. Yeah, so with that, I mean, that's mostly what the performance optimization section of this module covers. So next, what we will do is we will look at the Vtune analysis, right? So far, we were just looking at Vtune analysis and then calculating just the summary report. So we will go a little bit in depth into how to look at all the rest of the stats that Intel Vtune Profiler, right? So since we are doing this on DevCloud, all we can do is like just look at the HTML report. So what we will do is we will load the local copy of Vtune Profiler and then see how we can see more analysis report, right? So for that, what we have here is in the main folder, we have a script to actually capture the Vtune data. So if you look at this script, you can see that we are trying to, we can change the matrix size to whatever. So let's try 1024, and then workgroup size is 16, and we are doing it on Gen 9 hardware, right? And then we can actually change this to maybe local memory version. Right, so to capture the Vtune output, so all we have to do is run that script. So here we can see that the one line that actually does the job of collecting the Vtune GPU hotspots is this one. We are asking it to collect the GPU hotspots, and then we are specifying a result directory, which is Vtune underscore data. And then we are specifying the actual binary with arguments, which is just this one, right? And then we are also specifying, I think, the size and the workgroup size. And once that is done, it's actually generating a summary report in the HTML format, right? So all of the data should be collected in this folder here, Vtune underscore data. So let's wait for a few more minutes until this is complete. So looks like it's 21% complete. So in the meantime, while this is still collecting the profiling information, let us know if you're seeing any issues. Are you able to, you know, run these optimized codes on all the different hardware? If you need any help with that. So here you can see that I've just logged in 3 different terminals, right, for 3 different hardware. So if you want, you can also run it just directly on the notebook. All you have to do is run this accelerator.py and then select the which device you want to run. So this might actually take a little bit of more time because it compiles and runs for every different hardware that you select. In this case, I've just have all 3 terminals set up right here so that it's just faster. So you can do it either way. So you can select whichever CPU you want. One of the reason I haven't logged into this particular CPU is because we don't have a whole lot of those CPUs on the dev cloud, so it might be difficult to access that. But these 3 should be available if you want to access. Right, so Let's look at this one. So it looks like, yeah, so it looks like this is complete, right? Um, so when this is complete, we should see Vtune local memory. See, this is the one, right, that was generated. It says it was generated 2 minutes ago. So if you double click on that, you will get the Vtune profiler information really showing what's the GPU time, what's the total time elapsed, and then we'll give you some basic stats about, um, you know, what is the FPU utilization, and then what was the most hottest GPU computing task. It's mainly the kernel. We have just one kernel doing the matrix multiplication, and then it shows you the time it's used, right? So this document just gives you basic information, but if you want more information, we have to install Vtune locally, which you can get from the Intel website on oneAPI based toolkit. But what we have to do is we have to open this particular folder, right? So I have actually installed Vtune on my local machine. What I will do is I will copy this Vtune data to my local folder and then open that, right? So to do that, what I can do is first I'll just zip that folder. So I can do, actually not here. I'll just do Vtune Gen 9. I think we use size 1024, right? So .zip, and then we'll be zipping everything that's in the data folder. So, right, so once this is zipped, that new file should appear right here. So this is the file that we just zipped up. So I can just right click and then download this entire zip file. And it looks like it's downloading about 11 megabytes. Okay, and we have the file right here. So I can extract that. Why it's not opening. Okay, so this is the Vtune underscore data folder that we have, and you can see that there is a Vtune underscore data.vtune file. So this is what we have to open. So if you have a local installation of Vtune, so you can open, so this will be the main screen. You can see that you can either open a project or you can open just the results. So let's click on open results, and then so the folder we are looking at is this one, the latest one, right? 1202. So here you can see that this also has a summary page, which we saw in the HTML report, right? So along with this one, we also get more information. Looks like this is loading, so you can see that memory hierarchy diagram, which is actually very important to analyze your code. This actually shows you mainly the bandwidth of memory bandwidth when using shared local memory, right? And also how much is between shared local memory and GTI, and also like the actual system memory, how much memory is being transferred. So this can be very good block diagram to actually quickly analyze how well your GPU is being utilized. It actually shows you how many execution units were actually active and how many were stalled, how many were idle, right? And the number of threads that were issued and the total FPU utilization, right? And same thing with the CPU as well. You can also see the actual kernel execution here, which shows you the global size that we used, 1024 by 1024, and also the local size. We used a workgroup size of 16 by 16. That also shows you the other performance metrics here, showing that 98% of the EUs were actually active, right? Shows you the peak EU thread occupancy, which is 100% in this case. And then we can also look at the summary page, and we can look at the other, for example, like L3 bandwidth and the shared local memory bandwidth as well. So if you have multiple kernels, those will all show up right here, one below the other. So mainly, there's also these timeline of different operations. You can see that during kernel execution, you can see that the exact location where the modules were created, and then where the event was like synchronizing with the host, right? So you can get more information on that. And this also gives you all the other memory bandwidth and then GPU access as well in this one. So you can use this panel on the right to either enable or disable any one of these. But the memory hierarchy diagram is, I think, a good snapshot that you can use to get more information. So let me know if you have any questions with the Vtune usage here. Yeah, so the script that we have here, Vtune, right? So it's mainly the way it works is it's actually it deletes the directory first, right? So the Vtune._data gets deleted, and then it starts collecting the information. So if you want to retain this one, so you can modify the scripts as it is. So the way we do it is every time you run this Vtune script, it actually deletes this directory and then collects fresh data. And then what we did here was just we zipped up the file, and then just we right click and then download it to your local computer. So one thing you have to note is that the Vtune version that is used on the dev cloud here should match the Vtune version you have installed. So as long as you get the latest version installed on your computer, this should actually work. Otherwise, there might be in some cases where some of the Vtune data you've collected may not open if you have an older version. So a simple way to check that is just do Vtune. That means where's version? Yeah, it just gives you the 2022.0.0, and you can check to make sure that you have the same Vtune version on your local computer. So as long as you have that, you will be able to open that. right? And then if you look at the Vtune analysis with GUI, right? So this is basically what this whole document talks about, how to use command line to capture the data, and then how to install Vtune on your local computer, right? It gives you a step-by-step instruction how to do that. And then once you've done that, you can download the result directory, and then you can actually use the GUI to open the results, right? And once you open the result, this document will actually go through step by step on how to analyze every tab options we have, and right, it walks you through. It also shows you the memory hierarchy diagram and how to analyze this one. Yeah, and I think this also explains the, how to see at every step of each kernel execution call, when the memory was being copied and when actual execution happened and when the synchronization took place, right? So we can look at where there is more time used up either in memory copy or in actual execution, and then that can be used to optimize your code. Let me know if you have any questions on this one. On Vtune or any of the performance portability stuff. I think, yeah, that's all the topic I had to cover. So mainly, so in the next week's session, what we can do is if you guys have any code that you're working on and are planning to make it portable for both CPUs, I mean Intel CPUs and GPUs, that is something we can look at, analyze, and then see what optimizations that can be done. That's something we can do as a hands-on working session, or if there's any specific topic that you're looking for that you guys need more information on, if you let us know before next week, we can prepare and then talk about those as well. Let us know what ideas you guys have. We will come back next week, and then hopefully we can have a more interactive session and more of a Q&A session.